Hi, welcome back. So we started this session a couple minutes after the scheduled time. We were finishing the previous session, and we are very happy to have you with us again. And we were finishing the previous session, and we're very happy to have you with us again. I think there is a problem here with the finishing previous session, and we're very happy to have you with us again. Yeah, sorry. I think there was here a problem with hearing on YouTube, and there was a short delay. So yes, we are happy to have you here again. And it is my pleasure to introduce the two speakers of this session. Steve Kirkland, who is our first speaker, is professor of the Department of Mathematics at the University of Manitoba. He's also the editor-in-chief of Linear and Multilinear Algebra, one of the main journals in our area, as you know. And today, he'll tell us about his research on disease invasibility on networks. We'll also have Professor Vilmar Trevisan. Vilmar Trevisan is professor of the Institute of Mathematics and Statistics at the Universidade Federal do Rio Grande do Sul in Porto Alegre. And he'll speak about recent results in eigenvalue location. And after the two talks, we'll also have some guests for a final discussion. So to have an informal end to our event. And it is my pleasure to invite Ángeles Carmona from Universidade Politécnica de Catalunya. She'll be here in this session with us. And Vlado Nikiforov, who was here yesterday, he's also joining us in the studio. And Zoran Stanic came quickly from the previous session, and he'll also join us in the discussion. So thank you very much for being here, and we'll get started. After each talk, we'll have questions. So, Steve.
Okay. So thank you, everybody. Thanks for that nice introduction, and also thanks to the organizers for putting together this interesting meeting. So my talk today is going to be maybe a little bit of an outlier compared to some of the other talks. I'm going to talk a little bit about an epidemic model on networks, but I'm really going to try and emphasize the application of ideas from spectral graph theory in analyzing this epidemic model. And so in particular, if there are any math bio people in the audience, I apologize because I'm going to be de-emphasizing a little bit some of the math bio details so that I can bring out the role of spectral graph theory in the problem. And so I'm happy to acknowledge and thank my co-authors, Zhixing Shui, Pauline Vanden Driesche, and Xuying Huang, who worked together with me on this project. Okay, so I'll just give you a little bit of context for the problem. So, well, perhaps this is topical. We're all thinking a little bit about an epidemic right now. So, but in general, imagine we have an outbreak of a disease. And that it occurs heterogeneously in several different geographic locations. So maybe the properties of the way the epidemic is evolving are different in different locations. These locations are called patches in the math bio literature, and that there's a possibility of movement between different locations. And so I'll give you a couple of examples, really more in the way of motivation. So one example we were thinking about is cholera, where that's a pathogen that's carried in water. And so you can imagine communities that are located along a river, for instance, and that the pathogen is carried between the patches, the communities, in contaminated water. Another possible example is an outbreak like SARS or COVID, where patches might correspond to cities, and then we have transportation routes that can carry infectious individuals from one patch, one city, to another. So that's the sort of background, and these are good things to think about as a model as we're going through some of the mathematical details. Okay, so as I said, the disease is maybe operating a little bit differently in each patch. It has characteristics that depend on where you are. And so these characteristics in the math bio terminology are things like the indirect transmission rate from pathogen to host, the pathogen decay rate, the pathogen shedding rate, that's sort of like a reproduction rate, and the decay rate of the infectious host individuals. So each of these characteristics are going to vary from one patch to another. We also have movement possible between different patches. And so I'll think of something like a finite number of, say, n patches. And I'll have a parameter m sub ij, a non-negative number, that represents the rate of say, pathogens dispersal from patch J to patch I. Okay, you can sort of see what's going to happen here. If I've got m patches and I've got these numbers, mij, so then I can construct what's called the corresponding movement matrix by just loading the values m sub ij into the matrix M. And then associated with that, we're going to have what I'll call a Laplacian matrix for obvious reasons. And so what do? I take the column sums of the matrix M and I string them out on the diagonal, and then I subtract off the matrix M itself. So I've represented that as diag of 1 transpose M, take away M, where that bolded one is the all ones vector in Rn. Okay, and so this Laplacian matrix will be familiar to those of us that work in spectral graph theory. And the way you can think about it is it's got some positive stuff on the diagonal, some non-positive stuff off the diagonal, and the way I've constructed it, the column sums of the matrix L are all equal to 0. Okay, and so just to emphasize the combinatorial side of things, I'll just say that there's a weighted directed graph that's lurking here in the background. Okay, the directed graph has an arc from vertex J to vertex I, exactly in the situation that M sub ij is strictly bigger than 0. Okay, so that's the movement matrix and the corresponding Laplacian matrix. All right, so here's a question that we care deeply about. Will the disease on this network eventually become extinct, or is it going to persist over time? And so it turns out that the answer to this question is determined by what's called the network basic reproduction number, and the notation here is R sub 0. So if R sub 0 is less than 1, the disease dies out, it goes extinct. And if R sub 0 is strictly bigger than 1, then the disease will persist. And so what is this number, this R sub 0, because it seems to be important? Well, I'll suppress some of the biological details, but when you boil things right down, R sub 0 is really going to be the spectral radius of a certain entry-wise non-negative matrix. Okay, so I've written a formula there. I've written it as rho of D1 times D0 plus L inverse times D2, and now I have to decrypt the alphabet for you. So rho, as I said, denotes the spectral radius. And these matrices, D0, D1, and D2, they're non-negative diagonal matrices. And in the kth diagonal entry, those diagonal matrices contain the patch-specific information that relates to patch K. In other words, they contain information about the transmission rate, the pathogen decay rate, pathogen shedding rate, and the decay of the rate of infectious host individuals for patch K. Okay, so just standing back and looking at this, this R sub 0, it turns out to be the spectral radius of a non-negative matrix. Okay, so that's good news because there's nice theory for spectral radii for non-negative matrices. All right, and so as I said, the disease we're thinking of as being heterogeneous across the patches, and so it turns out that each patch has its own basic reproductive number. I'll call it R0 super K, and it's based on those patch-specific parameters. And it turns out, so this is some work in the math bio literature from a few years ago, if the dispersal between the patches, the dispersal of individuals between the patches is faster than the disease dynamics, then it turns out that this network basic reproduction number, R0, is nicely approximated by the following expression. It's a sum from k equals 1 to n, u sub k, r sub 0 to the r sub 0 super k, those individual patch-specific reproductive numbers. And what's inside this, what are these u's? Well, the vector u1 through un is the right null vector of the Laplacian matrix that we saw before, normalized so that the sum of the entries in U is equal to 1. Okay, so I'll just pause and make two comments here. So I said earlier here, I said the hypothesis here is the dispersal between the patches is much faster than the disease dynamics. So in the cholera example, you might think about that as being something like the movement of the water is very much faster than the pathogen decay rate as the pathogen is sitting inside of the water. Okay, so that's one comment. The other comment here is that this approximation symbol here, this essentially is saying that the dispersal rate relative to the disease dynamics is going to infinity. I'll be a little bit sloppy later on, and I'll write R sub 0 equals, but in the back of your mind, I want you to bear in mind that this is really an approximation. Okay, so what we're saying here is we can consider the network reproductive number as being built out of a weighted sum of the individual basic reproductive numbers, R sub 0 to the k running from 1 to n. Okay, so a couple of good things about this expression. So number one, the vector u. Okay, so that's a null vector for the Laplacian matrix. So that depends only on the structure of the network itself, okay, or equivalently the weighted directed graph that we're thinking about. It doesn't depend on the disease dynamics. Okay, and so what that means is we can study the influence of the network structure on R sub 0 as a thing on its own. Okay, and so here's, in my mind, that's why an advantage. So you might be in a setting where you're trying, for example, to control the spread of the epidemic. And so you might not have very good control over the level of invasibility on the individual patches. Okay, but you might have better control over the structure of the network that connects those passages. And so the airport, a network of airports might be useful. Okay, might not have good control on the invasibility of the disease in a particular patch, but you do have the ability to control movement between the patches. And so this idea that we can analyze the influence of the network itself might have some utility built into it. And what would a change in the network look like? Well, for example, in an airport type network, we might control the number of people that are allowed to move from one spot to another. In a cholera setting, it might, for example, be something like a flood connected with a river. All right. So here's a little toy example to sort of get your interest in the kinds of problems we might be interested in solving. So here's the setup. I've got a little network on 4 vertices. Okay, I've got directed edges. It's essentially a path-like construction here. And so the diagram on the left, I've got one vertex in red, okay, vertex number 2. And so here's what I'm thinking about. I'm thinking that R0 super 1, okay, the basic reproduction number for vertices 1, 3, and 4, those are all equal to each other, but that the reproductive number for vertex 2 is very much larger. I think in this example, we took it to be 10 times larger. So we can think of vertex number 2 as representing a hotspot for the disease. And now the blue arc on the left-hand side there indicates that we're going to increase the possibility of movement from vertex 1 to vertex 3. And I just want to see what happens to R sub 0 when we do that. So we look at the graph on the left-hand side, and what we see is R sub 0 is decreasing as we increase the possibility of movement from vertex 1 to vertex 3. Okay, right-hand side is the same sort of thing. The setup is exactly the same. Okay, the red vertex number 3 has a reproductive number that's 10 times larger than that at vertices 1, 2, and 4. And now we do the same sort of thing with the arc. We increase the movement from vertex 2 to vertex 4. And now we see completely opposite behavior. Here, R sub 0 is increasing as we push that movement from vertex 2 to vertex 4. Okay, so that's the kind of thing where clearly the structure of the network is influencing the behavior of R sub 0, and it's the kind of thing that we're trying to understand here. Okay. And so what I want to do now is explain how we can use some tools from spectral graph theory to really come to grips with this R sub 0. Okay, so imagine we've got a weighted directed graph associated with the movement matrix, and let's suppose for simplicity that that this digraph is strongly connected. And so that means our Laplacian matrix is a singular and irreducible M matrix. Okay, and so by Perron-Frobenius theory, of course, there's a unique right null vector U whose entries sum to 1. Okay, and that's the kind of thing we're trying to get at here, because those entries in U are influential on the expression for R sub 0. And now what I want to do is I'd like to perturb the movement matrix M to some other movement matrix, say M tilde, where the digraph for M tilde is still strongly connected. And that's going to give us a new Laplacian matrix. I'll call it L tilde. And so the kind of question we want to answer is, what's the structure of U tilde? So that's the right null vector of L tilde, normalized so that its entries sum to 1. And then in terms of a control strategy, is there a good perturbation M tilde so that when I look at the new value of R sub 0, which comes up by looking at the weights from U tilde, that's somehow smaller than the original R sub 0, because we'd like to decrease this value R sub 0. All right. Okay, so we can take a combinatorial view of this vector U, and that actually turns out to be useful. So remember our Laplacian matrix L, it's singular, it has 0 as an algebraically simple eigenvalue, and so if I just take L and I multiply it by its adjugate matrix, so it's a matrix of cofactors, of course, that's equal to 0, and that's also the same as if I took the product between L and the adjugate the other way. And so what we find out is that the adjugate matrix is a scalar multiple of the outer product of this null vector U with the all ones vector. Okay, and so what does that say? It says the entries in U are proportional to the principal minors of L of order n minus 1. Okay, and so I'm gonna recast that last statement in a more combinatorial fashion. let C sub k be the principal minor formed by deleting the kth row and the kth column of the matrix L, then C sub k is the following sum. I hope it'll look familiar to you. So it's a sum over well, I've called it T in T sub k. So T sub k is the set of spanning in trees. They're rooted at vertex k. So all of the arcs in each of these in trees points towards vertex k. It's a sum of weight values, and these W of T's, these are just the products of the edge of the arc weights in the in the spanning in tree T. Okay, so what we're seeing is that this C sub k is a sum of weights of spanning in trees. Okay, so I haven't said anything mysterious to a spectral graph theorist. What we're really talking about here is a directed and weighted version of Kirchhoff's matrix tree theorem. Okay, great. So we have a combinatorial way of trying to understand what's inside of these vectors, what's inside of the entries of this vector U. Okay, and so putting it together using that combinatorial viewpoint, we see that U sub k is C sub k divided by the sum of all of the CLs. And so then we want to try and analyze that a little bit. So for example, if I fix an arc from J to I in the corresponding directed graph, then I can think of these weighted spanning in trees in two ways. I'll let W sub k super ij. Those will be the sum of the weights of the spanning in trees that are rooted at k that contain the arc from J to I. And then I'll have W sub k tilde ij, and that's the leftover part, right? So that's the sum of the weights of the spanning in trees that don't contain the arc from J to I. And of course, C sub k is just the sum of those two things. And then you just do a little combinatorial argument. If you want to figure out what the sign of the derivative of U sub k is with respect to M sub ij, it's just the sign of a particular expression that you get by looking at these different weights. So it's the sign of W sub k super ij times the sum of W super L of the tilde ij's, where you run the sum over indices L different from k. Take away essentially the other way around, W sub k of tilde ij times the sum of the WL ij's. Again, L's running from 1 to n different from k. And from there, it's an easy conclusion to see that the derivative of U sub k with respect to M sub ik is strictly less than 0. And essentially, it's because this term here, the W sub k ij, when j is equal to k, that term disappears. Okay. So these are not difficult combinatorial arguments. It's just a matter of thinking about these spanning in trees and what their structure looks like and tracing through the details. And so, for example, the kind of combinatorial approach that I just described could be put to use into analyzing the derivative of our approximation for R sub 0 with respect to a particular entry M sub ij. Okay, good. So that's one way we can use spectral graph theory techniques to get something interesting in this problem concerning R sub 0. I want to take a more of an algebraic viewpoint here. I'll try and connect it back up to the combinatorics in a minute. But let's think about our Laplacian matrix L. Of course, it's not invertible because we're talking about null vectors, but it has what's called a group inverse. So that's a matrix L sharp, and it has the following three nice properties. L commutes with L sharp. If I take the product of two L's and one L sharp, I get L back again. And if I take the product of two L sharps and one L, I get L sharp back again. These are natural things that you might want out of a notion of an inverse. It's a generalized inverse. And it turns out that L sharp times L can be written as the identity matrix, take away the outer product of our good vector U and the all ones vector written as a row vector. Okay, so that basic fact can be used to address the problem I posed before. So imagine I have two Laplacian matrices, the original Laplacian matrix L, and then a guy I'll call L tilde. Okay, so L tilde I'll write as L plus E. So E is some perturbing matrix. We think that L and L tilde are still both irreducible Laplacian matrices. And I'm going to write out U and U tilde as the respective right null vectors normalized so that the sums of the entries in each vector are equal to 1. Okay, so here's a really helpful formula. We have an explicit expression for U tilde as I plus L sharp E inverse times U. Okay, it's not very hard to show. If you're familiar with some of the perturbation techniques for Markov chains, you'll recognize the formula. It comes up in other contexts as well. And so here's what we can do with that formula. Imagine we're going to do the following thing. Imagine we'll take, we want to perturb the movement matrix M so that we say, let's say we increase M sub ij. We're going to increase it up to M sub ij plus epsilon. Okay, so what that means is that this L tilde is in fact just a rank 1 perturbation of the original Laplacian matrix L. That means that this error matrix capital E that was on the previous side, that's rank 1. Okay, and so then we can use the Sherman-Morrison formula for the inverse of a rank 1 perturbation of the identity matrix, put it together with the formula for U tilde, and come up with a closed form expression for the difference in the kth entry between the vector U tilde and the vector U. And there it is. And I don't want you to look too closely at it, but it's built out of the obvious things. It's built out of epsilon. It's built out of the entries in L sharp in the kj, ki, jj, and ji positions. And it has an entry, I think that should be an entry U sub j as well. Okay. So easy consequence from there is another way of getting at the derivative of the kth entry in U with respect to M sub ij. But even better, we have a closed form expression for R0 tilde. Okay, so that's the network basic reproduction number for the perturbed movement matrix. Take away R sub 0, the network reproduction number for the original movement matrix. And it's this alphabet soup here. But again, what I want you to observe from the formula here is it's built out of the information that's inside of L sharp, as well as these guys here, the basic reproduction numbers at the individual patches. Okay, and so I feel like I have to sell you a little bit on this matrix L sharp. I agree it seems a little mysterious if you're not used to it at the beginning, but I'll just say the L sharp can be computed from picking your favorite principal submatrix of the Laplacian of order n-1, inverting it, and then doing a few low rank adjustments to get your answer. And of course, the inverse of an n-1 by n-1 principal submatrix of L can be computed from the cofactor matrix. And so that means we have to know something or other about the minors of the matrix L, but those minors themselves admit a combinatorial interpretation. If you're familiar with the all minors matrix tree theorem, you find out that the minors of the matrix L can be written as sums of weights of certain spanning in forests in the directed graph associated with L. Okay, so even though the L sharp comes up in, say, an algebraic setting or even an analytic setting, because we're talking about L-sharp for a Laplacian matrix, there's embedded within it a bunch of combinatorial information about the underlying weighted directed graph. Okay, so I want to go back to a little bit of an example. It's related to the example that we looked at a little while ago. So this is a network with a hotspot, okay? So I've got a strongly connected directed graph on vertices 1 to n, and let's suppose that there's a special vertex, which we'll call vertex L, with a property that the for each k different from L, R sub 0 super k takes a common value, R naught, okay? And that R sub 0 super L at the hotspot is strictly bigger than R naught. Okay, and so we want to select indices I and j, and let's suppose we want to increase m sub ij by a fixed amount. Okay, we want to increase it by epsilon. Okay, so you just do a little work with the earlier formula that I gave you. There's some small simplifications that come up, and you get for this special sort of perturbation. R naught tilde take away R naught is this expression here, right? And so what you see is that you've got a simple-ish expression that you need to analyze. And so as a possible control strategy for trying to decrease the value of that network reproductive number, one of the things you might do is try to pick indices I and j so as to maximize this quantity here. Maximize because I've got a minus sign and a positive number out front here, so I'm trying to decrease the network reproduction number as much as possible. And so I'll give you a little example. It goes back to what we looked at before, the toy example of those two graphs I showed you. So here's an example. So this is, well, you all recognize the Laplacian matrix for a path. As nice a Laplacian matrix as you might want to meet. And let's suppose that vertex L is a hotspot in the way I mentioned to you just a couple of minutes ago. All right, so you can go through, you can actually produce a closed form formula for the entries in L sharp. I won't give you the horrible details, but I'll just say you can analyze L sharp, and here's what you find out. If the hotspot L is bigger than n plus 1 over 2, then the quantity of interest, the one you're looking for, is maximized when I is equal to 1 and j is equal to L. Okay, so that corresponds to adding an arc in the directed graph that goes from vertex L, the hotspot, all the way out to the pendant vertex number 1. Okay, and here's the maximum value of this expression in that setting. On the other hand, if L is less than or equal to n plus 1 over 2, then the same expression is maximized when I is equal to n and j is equal to L. In other words, we're taking an arc from the hotspot L and orienting it towards the other endpoint of the path, the pendant vertex n. And again, there's the maximum value here. And so what you're learning from that is that, I mean, the lesson there is, if you've got a path and you have a hotspot at vertex L and you want to decrease the network reproduction number as much as possible, you should take an arc from L to the farthest endpoint of the path and put that directed arc into the network. Okay, and the same sort of analysis that we went through with the path also helps to explain what happened in the picture that I showed you earlier on in the talk, where we had those different behaviors for the different types of arc additions into the digraph. Okay, so I'll wrap up quickly here with just a couple of final thoughts. So So I'll just say that this epidemic model on the patch network has analytic elements, and if you want to go into the details, I'll just do a little spoiler alert. There's a system of differential equations that's underneath the hood here, and that's driving a lot of it. But it also has, for we spectral graph theorists, it also has some combinatorial structure that's interesting. Using this approximation for R sub 0, we're able to sort of parse out the underlying influence of the directed graph on the problem, and we can see how the digraph affects the value of R sub 0. And how do we do it? We use some really straightforward techniques from spectral graph theory, especially the Allminer's matrix tree theorem and its variants. These are key tools in our approach to these things. And in my view, the group inverse, this L sharp, has an important role to play here, and it helps to inform these network-based strategies for decreasing the invasibility of the disease. So thanks very much for your attention.
Thank you very much, Steve, for the very interesting talk and for having us know this new matrix and L sharp. We have a question from the audience. So Amit Shidani asked if we can determine a minimal set of routes, which after removing them can make R0 less than 1.
I mean, we didn't do it. It's a great problem because it goes exactly to what I suggested earlier. You're trying to use the structure, you're trying to affect the structure of the network in such a way that you can decrease the R sub 0 value. So it's very much a natural question, and I think getting into the details with this L sharp is the way to do it.
Nice. And I have a question from Nair. She asked it from the studio, so it's not on YouTube. Okay. And she asked whether you applied this theory in some real situation. And then I will add to the question, right? We are having this COVID pandemic, and if this modeling could be applicable to some model in this direction.
Sure. So we have not yet applied the theory to the real situation. It's something that I think that would be fantastic to do. To be honest, one of the most difficult parts of that kind of thing, and the mathematical epidemiologists know this very well. It's just getting the data and getting the right kind of data. Actually, I've got friends who are working on COVID, and they're doing sort of nightly downloads of data from Johns Hopkins, and then trying to, groom it in such a way so that it's not so noisy. So I think there's a lot of pre-processing that has to happen. But yes, if we can get our hands on the data, that would be fantastic. And Carlos, yeah, I think there is room for a COVID-style discussion here. I mentioned SARS earlier, and it's a similar sort of thing. You've got for SARS, it was a transportation network with people moving into the network, going from one patch to another and bringing the disease with them. So yeah, I believe it's applicable in that case.
Very nice. We have another couple questions coming from YouTube. So Mohammed Fakaran asks about the multiplicity of Laplacian eigenvalues related with
so that's kind of interesting. So a couple of things. This L sharp is intimately connected with the eigenvalues of the Laplacian, because one of the ways for computing it, for example, is via the Jordan canonical form for the matrix L. Multiple eigenvalues are going to be a problem, quite frankly. Remember, in general, your network is directed, so you're going to have, you've got a 0 eigenvalues, but in general, you'll have a pile of complex eigenvalues as well. You're not going to have necessarily diagonal diagonalizable matrices. You might have some complicated Jordan form, and we know from if you live in the world of numerical linear algebra, you know that complex multiple eigenvalues with complicated Jordan structures are very, very unhappy for computation. And so yeah, there could be an interesting question there about how imagine you computed L-sharp in that setting where you thought you had high multiplicity for Laplacian eigenvalues. How confident are you that your computed value of L-sharp is actually close to the real thing? Yeah, so it's a good practical problem.
Thank you very much. So I still have another question, and then after that, we'll defer further questions for a later part of our broadcast. But Gail Dahl has a question about analytical control.
Hi, Gail. Nice to see you. I believe so. So when imagine if your tree is nice enough, then you should be able to get at a closed form for this L-sharp, and then you have quite a bit more information on what these entries of L-sharp are looking like. And then I agree, then you've got a shot at that point of being able to start doing, having a sort of analytical approach to network control. Agreed.
And I saw a final question here, actually, in the internal chat here. Danielle Jaume asks if the model could be used to study forest fires and other contexts like this.
Yeah. So I think probably the answer is yes, although I have to confess I haven't thought about it, the forest fire technique. But as I said, the idea is to go, under the hood here, there's a whole system of differential equations, right? So and in the end, okay, so maybe we're modeling a pathogen, but maybe it doesn't matter whether it's a living organism or something that's still dynamic like a forest fire. So I think the answer there is to go back, dig into the original system of DEs and see how much does that apply to the forest fire context, and if so, then off you go. Again, as I tell my non-mathematical colleagues, the great power of mathematics is abstraction and rigor. And in the end, if we can solve a whole bunch of problems, diseases, forest fires, whatever, all in the same mathematical framework, that's the power of our discipline.
Thank you very much. And yes, on behalf of all the organizers, it was very nice to have you talk here to us. And so I'll ask and introduce Vilmar Trevisan. Hi, Vilmar. And
hello.
Vilmar, you need to look at your presentation.
Is it okay now?
No, I think you're watching StreamYard, and you should be looking at your slides.
I'm looking at my slides, Carlos.
Okay,
Wait.
so no. So we'll have to share again.
Okay.
So yeah.
Share.
Just a short while, like those kinds of events have those things, and yeah, that's how it works. And I see that there are a few other questions here on chat that we haven't addressed so far. Later on, we can come back to them. Okay, I think now. Okay, now
Is
yes.
it coming?
Now it did come. Yes. So.
I put full screen now.
Yes, it's on full screen and it's all good to go. So,
okay.
Vilmar, please go ahead.
Okay, thanks. Well, thanks for the organizers of this session to invite me. I'll talk about some late problems that we have solved using some technique that I call locating eigenvalues. So the idea here of this talk is the following. I'm going to say something about locating eigenvalues of trees, and I will show you how some recurrence relations appear when this algorithm to locate eigenvalues for tree. And finally, we will show how we, looking at these recurrence relations, we solve some problems that were hard in the beginning. So the outline is this. I'm going to say what is locating eigenvalues. I will say something about the tree algorithm. I will tell how these recurrences actually appear, and finally the applications I want to tell you about. Okay, so locating eigenvalues of a matrix simply mean that we determine the number of eigenvalues that this matrix has in a given interval. This is simple. Now, in our view, what exactly do we want to do? We want to find a diagonal matrix that is, we want to diagonalize a matrix that is associated with a graph. And it's important that we want to use the structure of this matrix, or the structure of the graph, more importantly. And then, of course, from the spectral graph theory point of view, we want to obtain properties of the graph. In our setting, we always find a real symmetric matrix. That means that A is diagonalizable and has an associated graph, has an underlying graph. So I'll skip this because it's obvious, right? I mean, two vertices are adjacent if and only if the edge associated with is non-zero, right? And for example, for this case here, we have this matrix here, and this is a symmetric, real symmetric matrix, and this is the underlying graph. Notice that the diagonal value can be anything here, 3, 4, and 1. Here we can think of as the weight of the vertices. Okay, and then this is important because then from this setting we have Sylvester law of inertia that applies, that says that whenever you have a real symmetric matrix, we know that this matrix is congruent to a diagonal matrix, and it means that the eigenvalues of A have the same signs of those of the diagonal matrix T. Here is the definition of a congruent matrix. Wait, here. Here is the definition of the congruence. So two matrices are congruent if there is an invertible matrix that satisfies this inequality here, right? Now, what does that mean? That means that if you find, what we want to do is more important than this. We want to design a linear time algorithm that diagonalizes a matrix that is associated to the graph. Say, if you have a symmetric matrix A, we associated this with a graph and consider the matrix A plus XY. Then, when we find this diagonal matrix with here minus X, then Sylvester law of inertia tells you that the number of positive entries of D is the number of eigenvalues of A that are greater than X. The number of negative entries of D is the number of eigenvalues that are less than X. And the number of zeros, the zero entries in D, is the multiplicity of X as an eigenvalue. Okay, so this is our setting. The main feature of this general idea, observe here, I'm not talking about the structure of the graph. I mean, this in general can be said for any graph, right? For any matrix that is symmetric. We want to keep congruence, I mean, while doing the algorithm. And how do you achieve this? We just perform elementary row operations, and then we immediately do the same corresponding column operation. So this keeps congruence. And this is important because because then we have achieved an algorithm whose running time is a polynomial in k times n here, and k is a small number of operations. And it is important here to realize that only reading a matrix has order n in square, so our algorithm has to be very effective. Now, this has been done. I mean, this locating technique has been done for trees, and this is the subject of this talk, mainly in application. This has been done with David Jacobs in 2011. So this is a 10-year-old algorithm. But there are other graph structures that has been worked on. So, for instance, this is a set of algorithms that do these locating algorithms for thresholds, for unicyclic graphs, for cographs, for graphs with small click width, graphs with small tree width, and finally for balanced for sign graphs. I mean, for unicyclic unsigned graphs. Okay, I mean, I am going to say very little about this algorithm, about the tree algorithm in this talk, and I will say how it can be applied to solve some nice problems. So, so as I told you, this is a 10-year-old algorithm, and my collaborator for a long time is David Jacobs. And okay, the idea is the following: we have a matrix that is the underlying graph is a tree, and then I am going to skip these technical details because otherwise I'll not have time. But it's very simple. I mean, I'll show you just the example here. If I'm going to use the matrix just to tell you how the algorithm works, to justify that the algorithm works, but eventually you will not use the matrix, because recall that if you use the matrix, we are going to store n square values, and we want to do better than that. So look, the idea when we have something like this, we have like Vj here has a child Vi in this situation here, and then we can in the matrix we have this situation, so we can use, if this guy is non-zero here, if this guy Ai is non-zero, we can use this to eliminate this guy here. This guy is L, the value of the edge between the child and the parent. So we can use this guy here to eliminate this using a row operation, and the same column operation eliminates this guy here. So eventually, if you do this operation, we come up with this, using this this Gaussian elimination. Now, of course, this works only if this guy is non-zero, but if this guy is zero, I'll leave these technical details here on the slides, but I'm not going through, because this is a kind of a trick. It's a nice trick, but it's no more than a trick. So when the value is zero here, if a child has value zero, we have to do something different, but we can do that. And the network, I mean, the final net of this algorithm is the following. So if we have a child that has a value zero, what do we do? Essentially, we put the value of this child as 2, the value of the parent that we are dealing with is -1/2, and if this guy is not a root, is not the root of the tree, if it has a parent, then we cut the relation. We cut the edge between Vk and its parent. And of course, I mean, if a node we are processing has child with all non-zero values, then we use the original thing, which is simply take the original value minus the inverse, minus the sum of the edge, the value of the edge squares over divided by the value of the diagonal value of the children. So, okay, this is the net algorithm, and recall that we start everything, I mean, the diagonal values are going to be dv is going to be dv plus x, where dv here is the diagonal value, the original diagonal value of the vertex. I'll do one example just to make sure that how this works. I mean, suppose that we have this tree here. This tree is a star-like tree with three rays here. So 1 and 3 and 3. This is the star-like tree, and we want to find out what happens with value x equal 1. So we want to know how many eigenvalues are greater than 1, smaller than 1, and equal to 1. So the algorithm tells you to start the algorithm with x equal minus 1. Everything, all the vertices are going to be minus 1 because the matrix we are dealing with here is the adjacency matrix. So everything originally has 0 in the diagonal. So 0 minus x is going to be minus 1. Okay, so this is the original configuration, the initial configuration. Okay, now we see the leaves are processed because we do not do anything with leaves. Now let's process these two vertices here. Okay, so these two vertices have children with non-zero values. So it's going to be this guy, which is minus 1, minus the inverse of this. So it's going to be 0 here, and it's going to be 0 here again. So these are processed. Now we need to go on and process these two values. Now, recall that since these two values here, we want to process like this guy here. Well, this guy has a child with value 0. So this child becomes 2, and this guy becomes minus 1. And we cut this edge here. Let's see if this is what happens. Okay, exactly. So this is 2, this is minus 1/2, and we cut this vertex here. Again, for the same thing here. And finally, we need to process this guy here, which is the root. So this is going to be, there is no 0 value, it's going to be minus 1 minus the inverse of this is going to be 0. Okay, so this is the final vertices, so this is the final values. This means that these guys here are the diagonal values of these, I mean, the values that appear in the nodes are actually the diagonal values of the matrix that is congruent to x, to the adjacency matrix minus 1. This means that since there are 5 negative values here, that means there are 5 eigenvalues that are smaller than 1. Since there are 2 positive values in the diagonal matrix, there are 2 eigenvalues larger than 1. And since there is 1, 0, there is a simple eigenvalue. I mean, 1 is a simple eigenvalue, which is simple. Okay, now, let's see how we can use this idea, this technique, to compare indices of trees. Well, let's see. Suppose that we have a matrix, right? I mean, here the matrix can be anything. The only thing that I need is that this matrix is associated with a tree. And supposing we want to compare the tree, the spectral radius of t and t prime. So here's the idea. We apply the algorithm to t with x, the index of the first tree, lambda of 1. So the Sylvester law of inertia tells you that all but one value is negative. One value is 0. And what is important here, this 0 happens at the root. I mean, we can prove that it's a matter of, it's an algorithm thing. Now, what do we do next? We apply the algorithm to the tree here, t prime, with the same value, the value of the spectral radius of the other tree. Now, well, there are a couple of possibilities, but suppose that one of these possibilities happens. If all the values are negative, this means by the algorithm that all eigenvalues of T prime are smaller than this one. In particular, the spectral radius of T prime is small. If all values that appear are negative, but one is positive, then you have the other around. We have that the eigenvalue, the spectral radius of T prime is larger than the spectral radius of T. Right, well, you see, of course, I mean, here there's some challenges because in general, you do not know the spectral radius of T or T prime. So, and of course, this simple idea may work if the trees are close to one another. There is not much difference. There is just a single, I don't know, a displacement or something. And of course, we need to have some technical tools, some analytical tools to do that, not numerical tools. And this is the idea. The rest of this talk is actually to apply the algorithm in a tree to see what happens exactly in a path. In particular, we want to see what happens in a path. And then I'll tell you how these recurrence relations naturally appear. And then we show how to obtain some properties of these recurrence relations using, of course, some analytical approach, transforming these recurrence relations into real functions. Okay, so the first example, and I'll show you exactly why these examples appear. I mean, they appear here in an organized way, but in real life, I mean, we're trying to solve a problem that I'm going to tell you later, and then okay, what happens if we apply here the algorithm for the adjacency matrix, right, of in the path, right? So, and with the spectral radius, so the initial value is the spectral radius, so it's going to be minus x in everything. So here z1 is actually just the spectral radius because it's a leaf. I'm considering that the root is somewhere over here. Z2 is going to be minus lambda, which is already there, minus the inverse of this guy here, because there is because we are applying the adjacency matrix, so everything here is just the inverse of that, and so on. Z3 is going to be. So the recurrence relation is simple. Here we have this recurrence relation that starts with minus lambda, and then this recurrence relation that is minus lambda minus the inverse of the previous one. Okay, I'll show you how this was used to solve some nice problem. Now, let's see a second recurrence relation. I apply the algorithm in the following tree. So the tree now is different, but I apply the same thing. Again, is the adjacency matrix. And we have the spectral radius of A. Now, if you think of this part of the tree here on the left before this spec here, this is exactly the same relation, same recurrence relation we had before. But if we look at from here, from, let's say, I call here B1, notice that B1 is going to be minus lambda minus 1 over Z1 and minus 1 over this guy here, because these are the children of this guy here. Remember, I'm going towards the root, so I'm going towards this side. And the general recurrence relation is exactly the same. Look, bi is equal minus lambda minus 1 over bi. So it's the same sort of relation, except that it has a different initial value. Okay, now let me call you the second or the third example where these recurrence relations appear. Now I consider a tree. I consider again applying to the algorithm a path of this tree, but now the matrix is the Laplacian matrix. So the diagonal values are the degrees. Now, and lambda is the average degree. So the average degree of a tree is this number here, 2 minus 2 over n. Great. If you do the, if you apply the Sylvester law of inertia, the number of negative values that are going to appear tells how many Laplacian eigenvalues are smaller than the average degree. And this is the problem we wanted to solve, right? Now, what is the relationship, the recurrence relation that appears? The recurrence relation that appears is this. See, the x1 here is 1 minus lambda because the degree is 1. x2 here is going to be 2 because that's the degree, minus x, minus the inverse of x1. So, in general, this is the general relation here. 2 minus lambda minus 1 over x minus 1 with the initial condition, this one. Now, okay. Of course, I put these three recurrence relations together because they are of the same time. We can see that all these recurrence relations are of this kind here. Xj plus 1 is equal phi of xj, where phi of t is alpha plus gamma over t. So here I introduce a real variable t here. So I'm going to look at these recurrence relations, just one kind of the same type, right? And again, I'm going to use this. Okay, so once you put these relationship together, let's see. I want to solve this kind of relationship. Now, this big result here, I'm just kidding a bit, it's just that it's a big result, but it's not so hard to put this kind of relationship, this kind of recurrence relation, into transform this into a second order linear recurrence relation. We do that, and then it's easy applying this, easy techniques to solve second order linear equation. We have three kinds depending on the discriminant. If the discriminant delta, if it is equals 0, then we have one solution. If it is greater than 0, then we have another solution. And if we have less than 0, then we have a different solution. It's important here, these guys here, theta and theta prime, these guys here are the same. Theta and theta prime are the same sort, and they are going to appear again. Now, once we have the solution, the general solution for these recurrence relations, right? For example, we use Z1 and Zi and Bi are these two recurrence relations here. They are all of type 2 because the discriminant here is greater than 0. Then studying this, we can show the following. Again, using here some analytical techniques. If we have Z1, the first value, is on the left of this theta prime here, this theta of this theta here. Theta depends on lambda, of course, and I'm thinking that lambda, lambda is anything, right? But in general applications, we have lambda as the spectral radius of the tree. Now, in any case, if you have the first value, the initial value, below theta, then the recurrence relation, the values of the recurrence relation, they increase monotonically, it converge to theta. On the other hand, if we have here the initial value between theta and theta prime, this fixed point theta and theta prime, if you have the initial value here, so we can show that decreases monotonically also to theta. So we have this sort of basing of convergence. Now, these are properties that are important, and let me just show some results. And I want to show that these co-authors, Vilmar and Trevisan, we studied this relation. The first recurrence relation was the first one that was somewhat simple and sort of triggered us to study this general recurrence relation. Using this, Dragan Stavanovic suggested this problem, and Vilmar was the guy who actually had this analytical look at this. We were able to order by the index all the star-like trees. So if we have if you give n, the number of vertices, we can order all star-like trees of n vertices in a total order. For instance, the largest, the partition or the star-like tree that has the largest spectral radius is this guy here. So this is the star. And the one that has the smallest one is the one that has only 3 rays, 2 of them 1, and then all the other ones in one speck. For example, for n equal 8, this is the order of the star-like trees. So 115 corresponds to this, and 111 means is a star with 7 rays, right? With 8 vertices and 7 rays is the one that has the largest eigenvalue. And in between, we know exactly how to order them using this. Studying this recurrence relation. Again, with Vilmar and Francesco Belardo, we studying this. We studying now the second recurrence relation that we know is also of type 2. We're able to show, for instance, several inequalities about spectral radiuses, and eventually we were able to show a total order of trees which solve a somewhat long-standing conjecture about the order of these trees. It's interesting that in this case we were able to do this ordering in a very, very tiny interval. So in the sense that I want to sort of tell you that it's impossible that any numerical technique should work, because this is a very tiny interval. So it has to have some analytical tools to do that. I'm not going to say much about this, but for example, one technique that I think it applies to our algorithm is about this technique may apply is actually for limit points. So limit points, Hoffman in 1972 asked how to characterize numbers, real numbers that are limit points of spectral radius of matrices, of symmetric positive matrices. And he himself showed that this is reduced to matrices that have 0-1 matrices, which means adjacency matrix of graphs. So this is a very important problem, and it's still studied. And of course, extending this to Laplacian matrices, this very little is unknown. One of the results that was proven, it was 2008, Gu proved that this tree here, so this is also a star-like tree. He showed that this, so star-like tree that has one ray with 1 leg, this ray here has n legs, and this also has 2 n legs. if you take n going to infinity, the spectral radius, the Laplacian spectral radius of this tree tends to this guy here. So 2 plus epsilon, where epsilon is the real root of this number. Okay, this proof is hard, and I'm not going to go to the details. I mean, but using our technique, I mean, using this idea of convergency, we can sort of quickly prove that. So in some sense, we can use this technique to make it, you know, a very easy proof, in fact. Now, I want to end this by just telling you the third relation that we analyzed. We just want to, you see, this third relation here is of the third type. So this discriminant here is less than 0. So but this is hard for one thing, because the initial condition actually depends on n. So it's not a fixed, it's a variational thing. The solution is periodical, so this is a much harder equation to deal with. And the origin of these recurrences is exactly because we want to show that the number of Laplacian eigenvalues that are smaller than the average degree is the majority. So for trees, the number of eigenvalues that are smaller than the average degree is at least half. That's the original, let's say, conjecture that we had. And again, here I'm not going to go through the details, but eventually we were able to prove this in a very recent paper. And again, here it is Vilmar Trevisan, David Jacobs, and myself have proven this. This was a very hard, and we spent a few years working on this. Okay, let me finish by saying some final thoughts about this. So what I wanted to sort of convey to you is that analytical properties obtained for the discrete recurrences enabled us to obtain some algebraic and combinatorial properties of the graphs. And I think it's important that we had an external look. There was an analytical approach to this. And I think my colleague Vilmar Trevisan, who actually, sort of looked into this with a different approach. Okay, now the applications we dealt with here are of the following kind. We find extremal trees for some parameter, spectral radius of sigma or something. Okay, given that we made, and we have location algorithms for other kind of graphs, I think it would be important to sort of get applications for these different graphs, not only for trees. Again, our algorithms are tailored for spectral graph applications, and I wonder if there are applications outside spectral graph. Finally, I want to say that we believe that locating eigenvalues is a good technique. We actually want to invest this. So much so that Carlos, David, and myself, we're writing a book about locating eigenvalues, and we have written quite a few pages already. You can see that this is the table of contents. We have about 170 pages already written. Well, 120 pages written. And this book is going to come out probably later of this year. Finally, I want to tell my Italian friends that I already miss Napoli. That has been my home for the last year. But I am in my permanent home here in Porto Alegre that also has some charms. So, well, thank you for your patience, and I hope I have not gone too over the time, Carlos.
Thank you, Vilmar, for the talk. No, it's fine. we have a couple questions here from the audience, and so I will post some of them for you, Vilmar. So one question here is about this conjecture about the Laplacian energy. So Masood.
Okay, I put, okay, let's see. There is a conjecture by Redan which showed that the upper bound holds for, yes. Not that I know of, right. I mean, yes, we have shown, and Carlos, I think, was our co-author in this, that the star has the largest, let's see, show that the upper bound, yeah, the largest Laplacian energy in trees, the largest Laplacian energy for trees holds for the star, and the conjecture is that the least Laplacian energy for trees holds for the path, and I don't think there is any good progress on this. Maybe for small diameters, but not really good progress on this. Not that I know of. But that's actually one of my favorite problems.
Vilmar, another question is by Mohammed Fakaran, and he asks about algorithms to find the multiplicity of eigenvalues.
Yes, there are. I mean, we have algorithms for I mean, the same kind of algorithm for cographs, for unicyclic graphs, and some other classes of algorithm. But recently, we sort of attack this problem in a more general way. So for any graph that has a click width that is limited, we can efficiently find algorithms, and the same for tree width. So even for general graphs, we have algorithms for this, but depends on this expression, for tree decomposition or click width decomposition. But the answer in general is yes. There are some other classes of graphs we can deal with. Yes.
Thanks. So, Vilmar, thank you very much for answering the questions. And I think it's time to move to the next, to the final part of our session. And Nair is back here. Hi, Nair. And we have also other invited guests who took part of the conference and already gave talks, and some collaborators who also accepted to be here. So they will join us here in the room. And so Vlado is here, and Zoran Stanic, and Steve, Daniel Jaume from Argentina. And so, Daniel, I think your camera is not on.
You can hear me?
Yes, we can hear you perfectly. So just the camera is not on.
Yes.
I think I have a problem because the camera is on, but I am here in my house isolated because I was COVID contact. So I can go to the university. In the connection in my house that is in the middle of the country here, Argentina, is not so good. So maybe yes, I'm going to be a black guy.
Okay, Daniel. We hope you're doing fine, although you're isolated.
That's fine. Let me tell you, I know where Daniel lives. I know where Daniel lives. It's really in the countryside. It's beautiful, but it's far away. I suppose the internet is not that good.
Oh, yeah. Well, thank you for the invitation. It's a pleasure to be here and to hear so wonderful talks and to learn so much. So I am happy.
Thanks, Danielle. So this session here is not something that we have prepared long in advance. So it's the part of the informal part of this event. So perhaps Nair could have a few words to say and ask some question, and then people at the audience could also ask questions for our group here.
First of all, I'd like to thank Steve, Vilmar, and Zoran, and Vlado, and Carmona, and everyone that could help us to a nice event. If you're not, I think it's nice, but I don't know. But the thing I would like to ask to provocation, I suppose, what would be the likely future of SGT research?
Oh, that's a very deep question. The future of SGT research.
We can answer everything.
Yeah. So anyone would like to give a try?
At the moment, what do you think about the future of SGT?
So I'll go out on a limb. So I think actually the future of SGT is really bright, especially if we spectral graph theorists are able to go out into the world and use all these fantastic tools that we've built to good effect in applied problems. Here's why I think that. So I'm kind of thinking about the big data thing, where we now have data sets that are so large and so complicated that essentially they can only be, a lot of them can only be represented as items that are related or not related, just because the data is so huge and so complex. So everybody knows that related and not related, that's just a graph. And so if we want to try and extract meaningful information out of these complex data sets, I think the spectral graph theory is the way to go. So, and what's great is that for many, many decades, we've been polishing the toolkit, we've been producing new tools, and I think it's really, it's a great time to be able to take those tools and apply them in these other settings.
Yeah, that's definitely a challenge, right? Angeles, would you like to say something?
Yeah, I agree. First of all, let me thanks for allowing me to be here and represent my research team. But I agree in the sense that the real world problems, like in PDEs and whatever, are very difficult to solve in the continuous case. So approximating in the discrete case will conduct you to a graph, no? And then you can solve the problem and come back to the continuous with the approximation. So that will be a good way to do. No? It's difficult because I think the language between the engineering or the language between the real world and our setting, it's difficult to understand each other. And it takes too long to understand what they want and what you can offer. But as mathematician, I think we should try.
I think it is possible that the people, that the researchers from linear algebra, graph theory, and algorithms, and it can be study graph spectrum. Could this be a tendency? Maybe. I know that the young people. I observed in several ILAS events that the young people likes the graph theory, spectral graph theory, because it's a play, it's a nice, it's a very attractive and intuitive way to see.
Yeah, we have the same feeling too, that in our university, many young people are interested, and they like the type of problems. And I guess, as Steve mentioned, there are a lot of practical applications that are close, and like also the last two talks have shown, combinatorial techniques appear a lot in connection with other problems, and with Angeles mentioned differential equations that show up, and Vilmar mentioned, we can use some recurrence relations that have solutions that people understand from dynamical systems, and that can be useful. So maybe this connection with the other areas is something that needs to be also developed, and has a lot of potential. I'm not sure, Vlad or Zoran, would you like to say something about your thoughts?
I would like to say very recent experience from last night. I read a paper which is already uploaded in the archive, but I'm not sure whether it appeared in the listings. It's about applying neural networks to combinatorics, and particularly to spectral graph theory, where it works for some reason very well. So it's really surprising to see things which we thought are for the future being applied to disprove conjectures which are just around us that we're interested in. So the author of the paper is a postdoc in Zurich. His name is Adam Wagner. He has actually written a previous paper where he applies linear programming, regular commercial packages, to disprove conjectures in combinatorics in general. But he says that his more novel thing is much better. Is better for spectral graph theory. So maybe we'll see some new things. So far, he's just looking for counterexamples to conjectures, but maybe it will be soon. There will be time that he's going to prove conjectures using the same neural methods, and that's not a very good development for all of us. So, yeah, that was something that I wanted to share, because last night I was thinking that I'm reading something from the future when I started reading this paper. So, that was what I wanted to say.
Yeah, that's very interesting. We should be careful about our conjectures, doubly so now. And but maybe in a slightly more optimistic tone, in the part of random graphs and things like that, people from statistical physics started applying methods, and they could find some thresholds to problems that were believed to be very difficult, and they work well, but they were not proved. So in that sense, the two communities kind of worked together, and mathematicians first saw arguments that were not so precise, and they got very impressive results. And it turned out that with a lot of work, it was possible to prove that some of these results were nice. So maybe it's a machine for good conjectures instead of a machine that doesn't need mathematicians to prove the theorems. Let's hope.
I would like to ask another question. The study of eigenvalues and eigenvectors of several graph matrices are being studied on graphs belonging to certain classes. This is a fact. Could this lead to a new area of matrix theory, such as special kind of matrices and its properties? I ask if the spectral graph theory can collaborate with linear algebra research, for example, in the back of the things that we do, because we use linear algebra, and maybe we can collaboration to linear algebra goals.
Many takers? That's a very hard question.
Because
I have my homework. I prepare my homework.
We use linear algebra more than to promote some new line. I don't know.
So I'd say briefly, I think the answer is yes. I think spectral graph theory does have a contribution to make to linear algebra, and there's already kind of a market for it there. So combinatorial matrix theory is a big discipline now. I mean, 30 or 40 years ago, it didn't even really have a name. But there are a lot of people working in that area, and it's in a way it goes back to the comment that Nair made earlier, that young people particularly are interested in graph theory. They're interested in linear algebra, and that's another domain in which those young people are attracted. And so I think there's definitely areas where spectral graph theory can make a contribution, like, as an example, minimum rank problems, for instance. Minimum rank problems are big in combinatorial matrix theory, but what's surprising is there are very few spectral graph theorists who seem to be working on it, even though there's kind of a natural connection there. So yeah, it's a matter, I think, of seeing. It's a bit like my earlier comment about applications. You've got to see where the spectral graph theory can help. And then you've got to be able to, as Anjali says, you've got to be able to come over to the other side and be able to speak their language a little bit. But there's definitely opportunities there.
Actually,
okay.
we have a specific
May
question.
I ask you?
Oh, sorry. Go ahead, Vilmar. Later on, we have a specific question from the audience.
I'm just, okay. Okay, fine. You may, but I want to ask you somewhat a different direction to put through a discussion to this. I mean, Nair and Steve and Vlado have given some future directions, I mean, in a very general way of problems. Let me ask the other way around. Okay. The thing is, for instance, I think some of the big problems are in spectrograph theory are, say, I don't know, the Brouwer's conjecture, if almost all graphs are determined by spectrum. These are two of the big problems. What I would like to ask you to throw a discussion is, do you think these problems, one, can be solved in the near future? And two, if they can be solved, do you think these are going to bring some new tools that are good for mathematics in general?
Yeah.
It's more difficult than my question.
In the meantime, while people think about Vilmar's tough question, Diego Bravo has a specific question to Steve, and it's about SGT and applications to big data.
Thanks, Diego. Now I'm regretting that I shot my mouth off. But to get started, I mean, I'm not going to get this right exactly, either in the name of the book or the pronunciation. But there's a researcher, Piet van Meyen, and he's written a book it's called something like Spectral Graph Theory for Complex Networks, and so it's actually not that recent. It's maybe 10-ish years old, but that's not a bad place to get started. Not because you're going to learn new spectral graph theory about it. I mean, if you're working in the area, you're not going to learn new techniques. But what you will learn is how are those techniques applied? What are the domains of application that the complex network theory people are interested in? So something like that might be a good place to get started.
And maybe Lovis's book, Very Large Graphs. So I think this book has potential answers to a few questions. First, because very large graphs came mostly from practice, and the theory is serious. It is not essentially spectral, but it has spectral aspects as well. So, and Lovitz goes over the spectral aspects as well. So this is complement to Piet van Meyen's book.
I think the computer science, for example, Daniel Spielman has used the spectral graph for draw, for partition of graphs or optimization problems like this. And I suppose that it's a strong area to go. I don't know, but I think that several people in computer science is think about spectral graph theory to use in your research.
I think also Fanchan is do things with real worlds and spectral graph theory.
Yes. I would like to ask another question about the young people that are watching us. I suppose that there are young people in the YouTube. Where can we find a list of good open problems in SGT? Where? Yes. Where in the internet some link? A long time ago, there were walls like this. There was a link called the wall in the graphs. I don't remember well.
Nair, I think you need to start a new project, Nair. You're good.
I suppose I invented to do, and maybe we can use some site to put several things of spectral graph theory and the open problems and the slides and the draws graphs. I suppose it's useful for everyone to use to do.
Yeah. We can do a web page, a Wikipedia specific for open problems. I don't know any place, a concrete place, specific place.
I don't know.
Yeah, I guess going to events. Checking new papers that appear.
We have to
the traditional methods.
Someone said that we'll go on an event like this. I suppose an Indian. I don't know. I don't remember the name. The professor. It's very, very known for. Yes, they say he said that he would like to organize an SGT Online soon, and maybe we can answer the questions for the next time, the next meeting.
Well, I have a question for the panel. That is, anyone knows about a model using spectral graph theory to model memory or learning? You know something about, or see a paper about that?
No.
I don't know.
The questions in the last time, it's not so easy to answer. It's so general.
So if you mean literally memory, I mean, I assume when you say learning, you don't mean machine learning. You mean actual real learning by humans.
Yeah.
Certainly there's work, people who study the brain are interested in, what parts of the brain get excited by different types of stimuli. And some of what they do with the data there is basically clustering. And we all know about spectral clustering. And those are some of the techniques, again, where the sort of old school spectral graph theory is making its contribution, because they're trying to understand which regions of the brain are connected to each other. So in that sense, there's SGT tools that are at work there.
Thank you.
Before we finish, I would like to also do, I think it's possible to go through we have to wait for the 3D machine, 3D impression.
Yeah, I saw this comment by Francesco Bellardo, and I think it sums up that we all hope that next time we'll be all together in presence. So I guess having an online event like that is something that allows us to invite many people that we couldn't invite for an event otherwise. So there is this big possibility. But on the other hand, presence is something very important. As our attempt to have an informal conversation, it's way easier having coffee, right, than being all in front of our cameras.
We can meet in Galway 2022.
I love to see everyone, and it's new afternoon, very, very nice in these pandemic times.
So I think it's time to say bye, and let's meet in the next event. Okay, so bye to everybody on the audience, and
bye.
I hope you enjoyed the event.
Okay.
Yeah, thank you very much.